Hello? Okay. Hello everyone. So today we're going to do a Math SL preparation. This preparation will run from 12:30 to 4:30. This is actually the first day of our SL prep. Tomorrow and the day after tomorrow, we're going to be running from 4 to 7. So stay tuned for that. Yeah, 4:30 to 7:30. So the content of our SL prep will consist of statistics, probability, financial applications, coordinate geometry, binomial theorem, and sequences and series last. Statistics was the most highly requested, that's why we're going to review it first. So yeah, let's get started. We're going to start with Jack, who's going to teach us a bit of statistics.
Hello everyone. Hopefully you can see this. Yes? Okay, I'm gonna assume that you guys can see this. So, statistics, it's all about taking samples of things, doing surveys, and then trying to get data and calculating like different information based on that data. So first, we'll get types of sampling. These are the 5 main types of sampling that you'll see, and what an exam will usually ask is which type of sampling is being exhibited here, or which type of sampling would be most appropriate. So simple random is the easiest. All of this is they pick a bunch of people on random to sample. Systematic is also pretty easy. It's like every 10 people in the group are the ones that you take data from. Convenience sampling is going to be a bit more biased, but it's going to be the easiest one to do with the lowest cost, and that's when you simply get the first however many people you see. For example, if you wanted to do a survey on like people at a playground, convenience sampling would be simply taking the first 10 people that you meet, whereas simple random will be taking a bunch of random people in that area. Stratified sampling is a bit more complicated. You'll need to do more. And what it is you stratify the people, so you select equal proportions from each subgroup. For example, if you were taking a survey at a school, you take, say, 10 people from every grade to get the subject. And then quota would be kind of like stratified, but it's not random. You take the first however many people until you meet a quota that you've set previously. So to run it back, simple randoms, the easiest, simple random is the least biased, convenience is the easiest, stratified has subgroups, and yeah. That's the central tendency. These are the mean, median, mode. Mean is the average value, and all this is say like data point. Say like if we're 1, 2, 3, or 1, 2, 3, 3. The mean would be 1 plus 2 plus 3 plus 3 over 4. To get the average, the median would be the middle one, so it'd be between these two, or 2.5. And then the most frequent value would be 3, as there are 2 3s. Next, our frequency tables. All you have to do is be able to read this. So this column outlines the store, whereas this column outlines the frequency, or how often it appears. For example, in the same sequence, 1, 2, 3, 3, the frequency table may look something like this, with 1, 2, 3, and then 1 appears once, 2 appears once, 3 appears twice. And then on the side here, you have if, that's simply store times the frequency. So we'll be skipping over these problems now because it's not very needed. Although this part is needed, is the variance. So variance is measuring how far apart the things kind of like differ from each other. So if everything was like 1, the variance would be 0 because they're all the same. Whereas if a data was like 1, 5, and like 9,000, the variance would be very high because the numbers are far apart from each other. And you can calculate variance with your calculator. Simply put in all your data values and then go into like calculate stats and do one variable stats, and one of them will give you variance. Next is a histogram. Just be able to know how to read these. Histogram are the bar graphs. Frequency polygons are pretty much the same thing, except instead of making the full bars like this, you only have the data points. And the next part is the frequency and cumulative frequency table. So with group frequencies, you have that the intervals are grouped together. So a histogram is really useful for this because these bars mean everything from like -1/2 to 1/2 over here, or 1/2 to 1.5 over here. So these bars already represent like the different sections or the different groups. And then the cumulative frequency is simply you add up all the frequencies of everything together. So you have 5 here, you add 22 to get 27, and then so on. And then your final value would be the number of total data points that there are. And this is really useful when you want to calculate something like the mean or the median, because for the mean, you can simply multiply your frequency by the child's height to get the data value out there. You add them all up for every single like group, and then you divide by the total number of items, which is already given in your frequency table. Think we'll probably skip this problem as well. All these notes are available on probably your link tree. We'll post it there, so you can come back and look at all of those. And then next is some more vocabulary. So remember when I talked about the different groups that there are? The class interval is the range of those groups. For example, if we go back to here, you see 90 to 100 could be one of the intervals. Or the range would be 10 because it's like from 90 to 100 is 10 values. And then the class center, that's the very center or the middle point of those. So when you make your histogram, those are the numbers that typically you'll be putting in. Or no, not the histogram, with the polygon. Those are the numbers you'll be putting in. Next are measures of dispersion, or otherwise, how far apart is the smallest and biggest and some things in the middle. So the range is really easy. It's just the highest value minus the lowest value. And then every single data point will fall somewhere in that range. The entire quartile range depends on the different quartiles. So the first quartile is the first 25%, second quartile between 25% to 50%, third from 50 to 75, and then the last quarter would be here. And the quartiles are like those fence states. So the minimum would be quartile 0, first quartile at 25, second at 50, or otherwise known as the median, and then last one at third. The entire quartile range, you'll see, will be this middle section, and all that is the distance between the first and third quartile. Next one, I talked about variance really quickly earlier, but we'll go over it again now. So there's two measures of kind of how spread apart the values are in terms of like each other. So standard deviation measures the spread around the mean. So it'd be all the values minus the mean and then take the average of that. And then the variance is the square of standard deviation. And variance is usually more useful just because it's always going to be positive, whereas standard deviation can potentially be negative. And then both these values you can calculate with your calculator. Just enter all your data into a single list or into a single table, and then calculate the one variable stats for those. Next ones are the bots and Whistler plots, and these appear very often in exams, I think, based on all the past papers I've seen. So all it is you have one side for the minimum, another for the maximum, and then the bots in between for the two quartiles. And then your range will be the highest value minus the lowest value. Your median will be the center line over here, and you can see like where most of the data is compared to the median, whether it's above it or below it. And then next is outliers. So typically you would have to make some defense for why a piece of data is an outlier, and especially you may have to do this given a bots and Whistler plot. So you want to find the interquartile range, that's the third quartile minus the first quartile, multiplied by 1.5, and then you want to have that value either below the first quartile or above the third. So what that might look like is if you have maybe a plot like this, you have the interquartile range here, and then you got 1.5 of that, so it'd be like around this size, and then it'd be above the third quartile and below the first quartile. So any piece of data that might fall over there, in this case there isn't any, but if there were data that far away from the first or third quartile, that would be considered an outlier, and outliers like impact a piece of data very drastically, so typically we'd want to exclude all outliers from calculations. Here's an example, and I'll actually go through this one. So let's start with the interquartile range. Remember, that's third quartile over here minus first quartile over here, so it's simply 7 minus 2, or 5. Given that k is an outlier, find the least value of k, and we're also given that k is greater than 7, or it's above the third quartile. So remember our outlier fences. We got our IQR, we multiply that by 1.5, and then we add it above the third quartile. So that'd be 7, which is the third quartile, plus 7.5, and that'd be 14.5. And you can see that 14.5 might fall under like around here, which is within the range of all the data, given that the maximum is 24. So everything over here would be considered an outlier, and we'd want to exclude that from our data calculations. I think I will now skip this one, although I should go over it here. We want to describe the distribution of the plot. So there's a couple ways that they want you to describe it here, and it's all based on skew, whether the data is more on the left side of the mean or median or on the right side of the median. So if there is more data on the left side or less than the median, that means it's skewed negatively. There's more data under the median than there is above. Well, under the average than there is above. And then positive skew would be the opposite, if like the stuff or size of stuff over here is greater than on the other side. So in this case, we can see that there's a negative skew. The median is here, and we can see there's a bigger range of data here than there is on the right side. Whereas if a plot maybe looked like this, it'd be positively skewed. Okay, and now is probably the most difficult part of this is coming to the normal distribution. So there's a couple ways of distribution before the normal, and we'll start with those first. So uniform distribution just means all outcomes are equally likely. So if we were to make a plot of that, it just looks something like this. All outcomes have the same frequency. Symmetrical means it's equal on the left and right. So you see side on the left is same as stuff on the right. Box plot, same thing. It's symmetrical. Histogram is approximately symmetrical. Over here, this is how to tell if it's positively or negatively skewed. Yeah, tell me any questions that there are in chat. So if we start with the mean over here, we want to remember that the mean is taken as the middle. It's not taken as like the center of the plot, but the mean or whatever measure of central tendency. So this is the center. Now if we take this as the center, we can see that there's some data over here, but there's a lot more data on the right side of the mean or on the positive side to the mean. So in this case, the data would be positively skewed. Whereas on the other side, if you go here, we can see that this is negatively skewed. Because once again, if we take the mean as somewhere, Bro, there's more, it's okay. The mean is over here, and you can see once again, there's a lot more data on the left side or the negative side than there is on the right side. Going back to the Botts and Worcester plots, we can see the same thing. If we take this as a measure of central tendency or as the middle, there's a lot more stuff on the right or positive side than there is on the other. And then same with this negatively skewed Botts plot. Next is clustering, is if there's a lot of groups that are kind of clustered together. And this doesn't really follow any type of curve that we'll see over here above. Instead, it may look something like this, or if we have like this, and then maybe another cluster, and possibly a third cluster like here. Next is bimodal. What this means is you can like break down the word. There's bi or two modes. So there's two very distinct peaks. Like in this graph, here's a pretty distinct peak, and then here's a pretty distinct peak, and there's not much in the middle. And sometimes bimodal graphs you'll see are pretty symmetrical, although they're not necessarily. Okay, and now we come to probably the most content or calculation heavy part of statistics. Is the normal distribution. So the normal distribution will look something like this. It's a classic bell curve, and it's defined by a mu value, which is the mean, and this sigma value, which is equal to the standard deviation. So the mean is the central point. We want to know where's the center of all this data. And then the standard deviation, it measures how wide or narrow the curve is. So if the standard deviation was really small, we'd see that most of the stuff are all grouped together. It's not a very wide or spread out curve. Whereas if the standard deviation was larger, we'd probably see something a lot wider. And the notation for this is x with this tilde in with a mean and a variance. Remember that variance is equal to the standard deviation squared. What this means is if we were to put a random x within this curve that is normally distributed with mean mu and variance sigma squared, this is what it would look like. If we were to throw a bunch of random variables, we'd see a lot more with frequency at this point than there would be at this value. And something to note is that a normal distribution defined by any mean and any standard deviation is pretty much a scaled up version of the z curve. So how does this work? It's because the z-store is measuring how many standard deviations a value is from the mean. That's simply the value minus the mean divided by the standard deviation. So if z-store is positive, that means it's above the mean. If it's negative, it's below the mean. If it's at 0, it is at the mean. And the standard form is with mean of 0 and mu of 1 squared. That means that any normal distribution curve can be kind of scaled down into something with a mean of 0 and standard deviation of 1. And this will be really useful for some problems that I'll probably go over later. Now, want to find normal distribution probabilities, and this is where your calculator comes into play. Let's start with normal PDF. This is returning the probability density at that exact value, or if we were a curve like this, and we want this point, it'd be approximately calculating what is the probability of this exact value happening out of 1. So that is to say, if we were to pick any random point on this curve or within this plot, what is the probability that we get one of this value here? And you can do this on your TI-84. It'd be going to second, vars, normal PDF, enter your mean value, enter your sigma value, and also enter the value you want to get the probability for. On your Casio, it'd be some kind of different. It'd be stat, press F5, norm, and then use NPD, normal PDF, or for the probability density at that single value. So how this works is within this normal distribution curve, what it's measuring is a bunch of data. So if we were to have a histogram of this, it'd be one piece of data over here, maybe 2 over here, maybe 3 or something over here, and then so on and so forth. If we were to pick a random point within just this part, let's say we wanted a value here, x. You can see that there's 2 data points over here, whereas there's 1, 2, 3, 4, 5, 6 total. So then your PDF would give something 2 out of 6 equals 1/3, or it would give it in decimal, so 0.3 or so. Next is CDF, and this measures the cumulative thing, so anything below or equal to that value. What does this mean in terms of the plot? It means that once again, if we draw the bell curve, and we wanted the probability of something being at this value or below, so any data point within this area, this is what the CDF is calculating. So it says here to enter your z-stores, but really you want to enter your mean and your variance. And then it can calculate for you what's the area of this portion, or what's the probability of this portion compared to the overall plot, which is considered as area 1. Next, on the TI, this is how you do it. Second, variables, normal CDF, enter your mean value, enter your variance value, and enter the value that you want to have, like the area below. So what this part is. On your TI 84, you're able to use bounds, so this is considered as pretty much 0, so everything left of that store. And then you have your other bound of this, which is considered to be like infinity, and be everything right of that store. Let me check this actually. Yeah, you're able, on the TI 84, you're able to set both a lower bound and an upper bound. Which means that you can actually calculate an area that's between 2 points, suppose something like this. This will simply be your lower bound, whatever value that is, and this will be your upper bound. And the problems that typically arise here is something like, given the normally distributed population with mean like 150 and standard deviation of 3, let's say this is like the heights of students in a classroom. What percentage of students are under like 154 centimeters? And then you go like, okay, well, it says under, so our left bound is going to be negative infinity. And then our right bound is at 155, so our right bound will be 155. And then we have a mean given and a deviation that will be given. And then Casio, it's like just different buttons to press. Once again, you have the different bounds you can use, with this being like negative infinity, this being considered infinity. It's going to stats, distributions, normal, and then you do your NCD or cumulative distribution and enter all your stores. That's okay. And once again, the difference between this is the normal CDF is anything within a range, so it can be multiple values, whereas PDF gives it at a certain value or a set value. And of course, you will be able to do the inverse of this as well. So this is called InvNorm on the TI. And what it does is, if you were given a probability and you were given a mean and a standard deviation, you can see what that value is. In other words, so I'll like draw it out here. Let's say your probability, you're given like this area is equal to 0.2. The probability of something lying under this value is 0.2. That'd be the area that you input. And then you have your mean that's given and a deviation that's given. And then when you calculate this, you'll be able to find what is this value such that the area is 0.2. Note that the calculation will only give you the things on the left side. So if we were this value, it will only give you here. Unless on, I think, the newest TI-84, you're able to choose between left and right. So if you were left, it'd be this, and then if you were right, you'll be able to calculate here. I'm pretty sure the Casio has the ability to choose left and right as well, and you can see that the buttons are here. And once again, you'll be able to have all these different notes. Okay, so I think before we go into quantiles and percentiles, I should go back to telling you why the z-store is so useful as a means of scaling something down. And it's particularly useful for when you want to find the inverse norm, when you don't have the mean or you don't have the standard deviation. So let's say you have some type of area, and so you want okay, let's say you have an area of like 0.3. The probability of being under something is 0.3. And you have that the mean is, say, like 150. this how it works? Yeah. Okay, let's say you have the mean is equal to 150, and then you have like a probability that it being under like 140 is going to be equal to like 0.3. And then what you want to find is the standard deviation. Well, we can break this down into z-stores simply by saying like 150 minus 140 over the standard deviation is going to be our z-store of this point. And then we have the probability of the z-store. So if we're to do inv norm of this z-store, let's call it z1, with area is 0.3, the mean is 0 in the z-store, and then you have our z-store is this, and our deviation is 1, we can find what our z1 is equal to. And then once we have like what our z1 is equal to, we can then get z1 is equal to, once again, 150 minus 140 over the deviation value. And then we can calculate our deviation as 150 minus 140 over z. So once again, how this works is if you have the mean, you have the area, and you have what the value you get is, you can calculate a z-store out of that in terms of the variable. And then you also are able to find what the z is based on the inverse norm of a z-curve with 0 and 1, and of area 0.3. And the same thing is applicable if you're missing a if you're missing a mean value and you want to have a standard deviation value. You would do the same thing. You have a z-store, let's say z1 is equal to your value minus your mean, so x minus your mean over the variance, or over the standard deviation. And then you can do your inverse norm with a z curve of 0 and 1 based on the area to solve for what the z is. And then since you'll be given 2 of the 3 of these values, you'll then be able to solve for the last one just based on algebra. Okay, and now for quantiles and percentiles, which can be, is it working? Kind of different. Okay, so percentiles, as per the name, is like percent. It divides the data into 100 equal parts, and the percentile tells you how much data falls below you in terms of percent. That means if you're at the 78th percentile, you're better than 78% of others. If you're within the 78th percentile, you perform better than at least 78% of all data values. And then quantiles would simply be the reverse of that. So quantiles would be like if you're within the first quantile, that means you're within the top 1%, and then at the second quantile, it'd be better than 2%. And the empirical rule here, I probably should have been moved earlier. It says that within a normal distribution, most of the things fall towards the center, with 68, 95, and 99.7 being the 2 things being within 1 standard deviation from the mean, 2 standard deviations, and 3 standard deviations of the mean. And once again, this is why the z-store curve is really useful, because all the curves will be basically a scaled up version of that z-store curve with 0 and 1. Let's do this example now. If a random variable is normally distributed with a mean of 120, so that means our mean is equal to 120, the following distribution shows the normal curve. And this shaded region is the area that we have, and the shaded region is equal to 0.4. What does that mean? The shaded region is equal to the probability of x being within that range. So we have that r is equal to 0.4, and it becomes really easy. So now that we have our one area, and we also have like 2 values, and we have the mean, we can then find the standard deviation, and then later find the probability that is below 135. I think I'll probably skip this for now, although I'll show you how you would typically solve it. So if we were to redraw this curve, we want to find this area. And we have area R is within 15. So if we want the z-store here is equal to 135 minus like 120 over the deviation, which is equal to 15 over the deviation. And then we can do the norm with area we have is equal to 0.4. And then we have our mean is 0, our standard deviation is 1. And then this will be a center tail, as we can see that is like within here. And then from there we can find what the z-store is. And once we have the z-store, we can then do like 15 divided by z equals the standard deviation. After we have that, we have all the needed data for this next part. We have both the mean equals 120, a standard deviation, which you would find later, and you have the x value that you want. And it'd simply be like CDF with the value 135, mean is 120, and then deviation is whatever you find from earlier, and it'd be a left tail, being everything is on the left side of that. Next, since you have all the data again, let's redraw the curve. It says p that x is greater than 105, given that x is less than 135. So what is the probability of this part given that it is like within this part? And all that would be is if this was R1 and this was R2, it'd just be R1 over R2. And notice that these are the two values that you found in part A and part B. Okay, and then another example problem doing kind of the same thing. Want to find k such that y is greater than k and is equal to the probability that x is less than k. So what that means is we want to find a value k such that with this info of like with a right tail, so CDF of 105, and that thing with the right tail is equal to CDF with 135 and that sigma value with a left tail. Let's see. Should I do this problem? Do we have time? We have so much time. Okay, I will do it then. Sure. Okay. Yeah, I'll give you like 3 minutes to solve then. Okay. I'm not sure if that's enough time, but we have a lot of content to cover. So yeah, if you didn't get it, you can try it again later. If you did get it, you can like now check with me, I guess. So the key here is once again like that Z store. Because remember, everything's like a scaled up version of that Z store, and the probability or the areas are always gonna be the same. What does that mean? That means that in this case, if we want y is greater than k, we're to draw like this, and then x is less than k, so something like here, these two. If they were to be the same, we'd see that the Z store, if this were the mean, this Z store would be the same as this Z store. And the reason this works is because like the normal distribution is both symmetrical and also because the areas are always the same. So let's write out our system of equations then, although it's only really one equation. So first thing, that y is greater than k. So let that value be, let's say, just like lowercase y. We get the Z store for zy would be equal to y minus, how do you erase? Oh, y minus 105 over your deviation value. And then similarly, yx would be equal to x minus 135 over your deviation value. I mean k, sorry. These values are k. K minus 135 over your deviation value. And the thing is that these z values are going to be negative of each other because one's above and one's probably below. So what that means is you get that k minus 105 is equal to, wait, sorry, they're not below, is equal to k minus 135, or negative k minus 135. And then if we want to solve that, we can get that 2k is equal to like, what, 235? And then you can solve that k is equal to 117.5. And that's how you would do the first part without using your calculator at all. Next one, given that the probability that x is greater than 130 is that, we want to find that py is between 90 and 110. And then what you should notice here is that this can no longer be a center curve because they're different distances away from the mean of 105. And so you'll have to calculate like the distribution twice, or the area twice. One for below it and one for above it. So we have p greater than 130 is equal to that area. Remember, we're trying to find our deviation right now, so we use the z-store strategy from earlier. And this would be the same as p that like a z-store is greater than whatever. I want to find what this whatever is. And that number can be found by 130 minus 135 over deviation. Yeah, and this is equal to 0.8944. So if you do our inverse norm right now of this, I'll just do it on my calculator right now. Get that the z-store is equal to negative 1.25 or so. So now we have negative 1.25 is equal to 130 minus 135 over the deviation. And we can find the deviation from there. Once we have the deviation, this part becomes like pretty easy. You'll just put it into your calculator with all the values that you have. Okay, now comes like more calculator work. We have a Pearson correlation coefficient and a Spearman's ranked correlation coefficient. And these are two ways to measure how close is the data to a single line. And we also have to probably talk about linear regression here. So Pearson's R-score measures both the strength and direction of a linear relationship between two variables, with 1 being they fit perfectly on an upward slope line, -1 being they fit perfectly on like a negative slope line, and then 0 meaning there's no correlation really at all. So what you want to do is you'd want to like have a table with like your data, and then with these two rows you can then on your TI it goes going to stat. You can calculate your two variable stats with the two lists, and it'll give you both and it'll give you the correlation coefficient. Another thing that's pretty important is you need to find the equation of the line that best fits these two values. So once again, you input your two rows as tables, and then you can go into your stat, calculate, and go into linear regression in terms of AX plus B, so that'd be number 4 on the TI. Do you know what it is on Casio? Okay. I'm not sure what it is on Casio, I'll like go back to that later. The Spearman's rank correlation coefficient doesn't really measure how straight it is. Instead, it measures how much it like consistently increases or decreases. So what does this mean? It means that you ranked all the data from 1 to like the last one in terms of highest to lowest, and you do your Pearson's correlation on that data instead, with a rank of 1 meaning it's always increasing. So it may look like either this, or it could also look like this. And then -1 would mean it's always decreasing. So it may be linear like that, or it may be like not linear but still always decreasing. So an example here, we start with the Pearson's product, or the Pearson's correlation coefficient. And all we have to do is input both of these values into your calculator, calculate the two variable stats, and it'll give you the correlation R. And then comment on the result. Typically, all you have to say is that the correlation is really close to 1, meaning that there's a strong likelihood of a positive linear correlation, or it's close to -1, so there's a strong negative correlation, or it's close to 0, so we can say that there's no linear correlation. And the next part is the equation of the regression line. So once again, after you have all your data in a table, on your TI you can go into your stats and calculate a linear regression. On your TI 84, I think, yeah, you can also calculate a linear regression based on these two lists. Okay, and next part you have to read carefully because it says to use the line of regression. That means that even if there were a data point within the table that has like serving 70 guests, you're not allowed to use that. You have to use your equation of the line. So this will typically give you something like AX plus B, and using our regression line serving 70 guests, given that the number of guests is X, it'd be something like A times 70 plus B, based on whatever values A and B you get from your calculator in part B. I think it's also important to note here that I'm pretty sure IB does have some partial credit for carry-through errors. That means if you made a mistake over here, as long as you use like the same values that you got wrong in here over here, you can still get credit for question C even though you did question B wrong. Okay. And then lastly on part D, it'd be like the same thing. You use your regression line equation to calculate for 50 guests. Okay. Then these two parts, I think we don't have the full question here because we don't have how much money that they are spending. Oh, that's okay. Okay. So that's probably all there is for stats. Really important thing is to remember how to do the normal distribution. Remember that all it is a scaled up version of this z-store distribution that's distributed with a mean of 0 from like -1. No, with a mean of 0 and a standard deviation of 1. And with that, you can calculate all the areas based on any data, because all the mean is doing is it's adding like some number to every data. So if the data were like 1, 1, 2, or maybe not that, but like 1, 2, 2, 1, you see the mean would be equal to 1.5, and all this is doing, oops, is it 1.5? Yes, it is. And all this is doing is it's taking like a standard of like between 0, and you're adding like 1.5 to every data value that would be like normally distributed then. So it'd be the same thing as like -0.5, 0.5, 0.5, and then -0.5, or like 3 here. It'd be the same as like adding a value to all of this, and the standard deviation doesn't change at all. Yeah. Okay, and then back down to our correlation coefficients. For our Casio, instead of going into our stats, calculate the 2 variable stats, is B2, which is stats. And then you put in all your data in a table. And then you go into your calc or calculation, and you want to calculate a regression based on x. And typically you want it in the form of ax plus b. That's most useful. Although I think for both calculators there's an option to select like a plus bx. Although I'm not sure why you would choose that. Just stick to your ax plus b. And that would be how to get the regression for your calculator. Okay, I think that's all there is for stats. If there are any questions, just like put it in the chat. Yeah.
Hi everyone. There's gonna be a 5-minute break before we start probability.
Okay, wait, just to say that again, there's gonna be a 5-minute break until we start probability. So just come back at 1:35.
Yeah.
And if you have any questions, put them in the chat so that we'll answer them before we start the probability section.
Okay. Hello, everyone. I hope you guys had a good time with statistics. So we're gonna start with probability now. What? The first thing we're gonna discuss is probability of an event. So the probability of an event is the number of favorable outcomes for that event out of the total number of all possible outcomes. So let's say, for example, you had 1 red ball, 2 black balls, and let's say they're all in a bag, and you draw one of those balls at random, and if it's a red ball, you win. So the number of favorable outcomes is 1, because there's 1 red ball. Out of how many total outcomes? Well, you could draw either the red ball or one of the 2 black balls. So it's 1/3. And this should be pretty simple. It's just review. And the important thing to remember for the probability of an event is that the value can only range from 0 to 1. You can't have a negative probability, because that would imply like you're literally like get that event a negative amount of times, and it also can't be greater than 1, because that would imply you get it like more than 100% of the time, which is impossible. Yes. And then obviously if the probability is 1, that means it's certain, and if the probability is 0, that means it's impossible. So we're gonna start with a quick little example. Bag A contains 4 red balls and 3 green balls. Bag B contains 4 red balls and 1 green ball. And part A asks, a ball is randomly chosen from both bags. Find the probability that they are of different colors. Okay, so first of all, we're going to split this into 2 cases. So first of all, we have case 1. We draw a red ball from bag A. And then obviously we have a green ball. Oh. Green ball from bag B. And then case 2 would be the opposite, because we also need that they are of different colors. So that would be a green from bag B, bag A, sorry, and then a red from bag B. And basically the way we're going to do this is, I'll just erase this real quick. So first of all, we're going to start with our first case. So we get a red ball from bag A and a green ball from bag B. So we're going to take the number of favorable outcomes. So 4 red balls out of 7 total balls. You just get that by 4 plus 3 equals 7 here. And then bag B contains 4 red balls and 1 green ball. So to select a green ball, you would need 1/5. That's our first case. This evaluates to 4/35. And for our second case, we have selecting a green ball from bag A, so 3/7. And then we're going to multiply that by selecting a red ball from bag B, which is just 4/5. And this evaluates to 12/35. And to solve this problem, what we do is we just add these 2 separate cases. And what we get is 16/35, which is our final answer. Our second question, I'm just going to read it out loud. So a biased coin is flipped. If heads is shown, a ball is randomly selected from bag A. If tails is shown, a ball is randomly selected from bag B. And basically what the problem is asking you to do is to complete the tree diagram below. So first of all, we have this box, which is unfilled. So we're going to go with that one first. So notice that we have a 2/3 probability of getting heads. 2/3 heads. And since our total probability for this column must be equal to 1, because you either get heads or tails, what we do is we just do 1 minus 2/3 equals 1/3 to get the probability for tails. Next, we're going to calculate the probability. Let's see. Yes. So we'll calculate this probability first. Over here. Let me just look. I'll just like write down how many balls each of the bags has. So 4 red, 3 green. That's bag A. Bag B, 4 red, 1 green. So the idea here to get the second one that I've just circled in red here is we use the same principle, 4/5, for getting a red ball from bag B. So that must mean we have a 1/5 probability of getting a green ball because you either get red or green. And then for the top, we're going to focus on bag A. So what's the chance that we get a red ball from bag A? Well, that's just favorable outcomes over total outcomes, which is 4 over 4 plus 3 equals 7. And similarly, we have green is 3/7. That's good. Now we're going to run over problem C. So the biased coin is flipped and a ball is randomly selected. Find the probability that the ball is red. So what we're going to do is we're going to note how many of these end outcomes turn up to be red. So in the end, we have these two outcomes. This one, and this one are both red. And using our multiplicative principle, what we're going to do is we're going to multiply the probabilities that lead up to that outcome. So we're going to start with this one first. This one, we have 2/3 to get the heads first, and then we have a 4/7 chance of drawing a red ball. So that would just be 2/3 times 4/7. And that is 8/21. And then for our second one, this one over here, second one, what we're going to do is we're going to multiply 1/3 for the tails and then 4/5 for the red. I'll just like circle them over here so that you guys can see. And this just ends up with 1/3 times 4/5, which is 4/15. And now our final probability is obtained by just adding 8/21 plus 4/15. Now at this point, a lot of people don't know how to add fractions, so I'm just gonna go over that real quickly. We're going to simplify everything to the common denominator, right? So that would be 105, I think. Yes, 105. Or actually, you could just enter this into your calculator and convert it into a fraction. So this would be, well, you can choose whatever method you like. All of them work. Equals 68/105. And let's see if the top and bottom have any.
Top is 2 squared times 17, so it doesn't matter.
2 squared times 7. Yes. Okay, so this would be our final probability. And our final part, given that a red ball is selected, find the probability that the biased coin showed heads. This is what we need to find, the probability that the biased coin shows heads. So, we can denote this as heads, given, that's what that line means, that red ball selected. And basically how we're going to do this is we're going to calculate, let's see here, in how many cases does the biased coin shows heads for whenever our red ball is selected. So first of all, we have this one, the second one that we evaluated earlier, the red outcome on the bottom. Well, that happens when we flip tails on our biased coin. So we have, this is a little bit disorganized, it's fine though. So this was our probability for the second one, which is tails. And this is our probability for the first one, which is heads. And basically what we're going to do is we're going to find probability of let's see. Sorry. We'll just write it down first. So our probability of heads over our probability that the red ball was selected. Oh, sorry, yeah. This should be heads and, so you denote that with this intersection symbol. It looks like an upside down U. Red ball selected. So as we derived earlier, this is a probability that a red ball is selected and we have heads. So the numerator would be 8 over 21. And in the denominator, we have the total probability that a red ball was selected, which is, as we did in part C, 68 over 105. And if you simplify this, which I'm about to do, 10 over 17, you get 10 over 17, which is a probability that the biased coin showed heads. So now we have a practice problem. Let's see if there's, okay. I'm gonna zoom out a little bit. Can everyone still see it properly? It's really small. Okay, so part C is a little bit hard, so we're just gonna go with parts A and B first. Since this is practice, we're gonna give you 5 minutes to solve this problem. Enter your answers in the chat, and we'll go over it once your 5 minutes is over. Thank you. Okay, guys. I hope you had a good time with that problem. Judging from the chat, it looks like no one solved it. So I'm just gonna go over the questions. First, for part A, right? We're gonna find the probability in terms of n that the game will end on her first draw. So first draw, what does that mean? The game ends when she draws a green marble, and there's 2 green marbles, so there are 2 favorable outcomes. And then how many total marbles are there? Well, that's just n. So 2 over n is our probability. Now, for the second draw, ending on the second draw, it's a little bit harder. On our first draw, we have to guarantee that we fail to win. So basically that means we don't draw a green marble and we draw a green marble on our second one. So to not draw a green marble, well, that's just n minus 2 over n, because there are 2 green marbles, so there must be n minus 2 red marbles because there are n marbles total. And then in our second draw, we have to draw the marble now. And careful, this is not 2 over n. This is not 2 over n, because since we've removed 1 marble from the box, this is n minus 1. And we have 2 green marbles, so multiplying this out, we get 2n minus 2 over n times n minus 1, and that is our probability that that the game ends on her second draw. In our second one, in our second part, the problem actually gives us an explicit value of n equals 6, and asks us to find the probability that the game will end on her third draw and fifth draw. So we're going to start with third draw. So as we did in part A, the strategy here is you need to fail to win on your first and second, and then win on your third one. So to fail your first one, since there are 2 green marbles, and there are 4 red marbles, to fail you have to have 4 over 6 total marbles. Now that you've removed 1 red marble, there are 5 marbles left and 3 red marbles left, so we get 3 over 5. And then on our last draw, we have to win, so that's 2 over 4, since we have 4 marbles left and 2 green marbles. So multiplying this out, 1 over 5. Now we're going to do the fifth draw. So essentially it's the same strategy. We're gonna fail on 1, 2, 3, and 4, and then win on our fifth draw. So what we get here is same thing here, 4 over 6 times 3 over 5. Now we're going to continue in this fashion. So there's 2 red marbles left. 2 over 4 times 1 over 3. And now we have 2 green marbles and 2 total marbles. So that actually means that any marble we draw on our fifth draw has to be a green marble. And multiplying this out, 4 times 3 times 2, you can just kill this. 1 over 15, and that is our final probability. Now part C, we're gonna give you a little bit more time to do part C because this is hard. The table is not drawn. I'm just gonna draw it real quick. What is it? Yeah, no, but there's like a blank page in the middle, so number, draws, and then money earned. I need 5. 1, 2, 3, 4, 5. And then 15, 4K. 10, 2K. And then on their fifth draw, you get 0. So we're going to give you 5 more minutes to solve this question. Please try it out. It's a pretty difficult question and definitely representative of what you see on a standard IB paper. Okay. So I hope you all had a chance to try out the problem. And the problem is actually quite lengthy, so I'm not going to go through the full details. But basically, to calculate the number of draws, you're just going to repeat the same strategy, and you get 5 over 15, 4 over 15, 3 over 15, 2 over 15, and 1 over 15 for the probabilities for each of the number of draws, respectively. And what we're going to do is we're going to calculate an expected value.
E is double slashed on the left side. No, the E has to. It's 2 lines. It's okay.
Dude, it doesn't matter. It doesn't matter. Okay, so the expected value is basically, in essence, we're going to multiply the probability of getting that outcome by like the value, which in this case is the money you get from that outcome. So for one draw, we have 5 over 15 times the value. What is the value? We have 15. Do I have to switch colors? It's fine. And then 4 over 15. Oh my days. I'm not Khan Academy, bro. Okay, it's fine. Multiplied by 4k. And then basically we can just continue like this for each of them. Plus 2 over 15 times 2k plus 5 times 0. And this is just 0. So we can ignore that. And if you simplify this, what you get is let's see. You get 105 plus 20k over 15. And the way to do this is basically just like collect like terms. It's really not that hard. And let's go back to the question. What exactly is it asking us? Let M be the amount of money that she earns back playing the game. Find the value of K so that this is a fair game. Since you pay 11 to play, you have to have an average outcome of $11 in order for this game to be fair. So what we're going to do is we're going to set the left side equal to 11. And then we'll just solve this equality. 60 equals 20k. And k equals 3, which is our final answer. And yeah. So now we're going to go over a couple other terms that you might need to know for the SL exam. So first of all, we have odds. So odds is different than probability. This is not probability. So going back to the example that we had at the very start, let's say we have a red ball and 2 black balls in a bag, and if you draw a red one, you win. So the probability here, as we've discussed before, is favorable outcomes over total outcomes. So in this case, we have 1 favorable outcome for the red, and then 3 total balls. So 1 over 3 is our probability. Now odds are different. Odds, you're basically considering the favorable outcomes to the unfavorable outcomes, not the total outcomes. So in this case, the odds would be the number of favorable, which is 1 red, right? And to the number of unfavorable outcomes. So in the 2 cases where you get a black ball, you lose. So those would be the unfavorable outcomes. And your odds would be 1 to 2, whereas your probability would be 1 over 3. So that's odds. Next thing we're going to go over is complementary events. Complementary events is basically the probability that event A does not happen, and it's denoted by adding a little prime. This is called a prime symbol after the A. And basically, as you can see below here, the probability that the probability of A plus the probability of the complement of A is equal to 1, which makes sense because event A either happens or does not happen. And similarly, by rearranging that, you can get this. A sample space, the set of all possible outcomes of a probability experiment. This one was basically like, let's see. So a sample space would basically be like, let's say you're taking two numbers from the set. So for example, there could be a question that's like, you're gonna flip a fair coin, let's say. So either heads or tails. And then you're going to flip another fair coin. And basically the sample space, you'd draw a matrix like this. Heads, tails, heads, tails. And then in each box, you'd put the probability of obtaining that outcome. So getting two heads, that's just 1/2 times 1/2 is 1/4. Same thing for one tail, one head. And then that is basically a sample space. This one is like not likely to be tested. But in the rare occasion that this does appear on the SL exam, you want to be able to know how to read the matrix and also calculate probabilities for each of the outcomes. Overall, like sample space, not a huge concern, but you should definitely review it. Next one, independent and dependent events. So this one is like pretty important. So two events are independent if one of them does not affect the probability of the other. And basically the probabilistic way, like with the actual notation, would be P of A intersect B equals P of A times PB. And this is equivalent to the statement that one of them does not affect the probability of the other. And an example of an independent event would be blood type and dominant hand, because what blood type you have does not necessarily affect whether or not your left hand or your right hand is dominant. And then dependent events is literally just when an independent event, it's just the opposite of an independent event. It's when the occurrence of one event affects the other. So for example, you have the probability of being late given that it snows. And obviously, if it snows, you're more likely to be late if you're driving, for example, because there's going to be like more cars, huge traffic, that kind of stuff. So in that case, those events would be dependent. Next up, we're going to go to mutually exclusive events. And these are events that cannot happen at the same time. So, for example, let's say you're flipping a fair coin, so either heads or tails. Mutually exclusive events would be probability of getting a heads and probability of getting a tails. Because obviously when you flip one fair coin, you can't get heads and tails. You can only get one or the other. So those events cannot happen at the same time. And then not mutually exclusive, same idea, just the opposite. Events that can happen together. And in this case, you can kind of draw a Venn diagram. So event A, event B, and then the middle section would be A and B. Yeah. So right now we're just going to go over an example involving everything we've discussed before: independent, dependent, mutually exclusive, that kind of stuff. So I'm just going to read out this question real quick. So two events A and B are such that A, U, B, so that U symbol means like A and B, or like either A or B happens. And over here we have that probability is equal to 0.78. A intersect B is equal to 0.27. And the probability of A given B is 0.45. And the most important thing to do first, if there's only two events, A and B, is to just draw the Venn diagram out, because this is extremely helpful in visualizing like how you should proceed with a problem. So we're gonna draw two events, A and B. So AUB is equal to 0.78. So this entire block is equal to, and basically what this involves is like all of this is A UB, and that's equal to 0.78. Now A intersect B, the middle part over here, A intersect B, that is given as 0.27. And then finally we have the probability of A given that B happened is equal to 0.45. So now, given this information, we're going to first find the probability of B in part A. So let's see. Okay, so first of all, what we're going to do is we're going to consider A intersect B. Of A intersect B is equal to 0.27. That's the probability in the middle. And now you have the probability that A, given that B happened, is equal to 0.45. So basically the idea is that if we were to use variables to denote this, let's say this is X and this is Y. Or actually, let's use Y to denote the entire event of B. Sorry, guys. Actually, no, let's just use X to denote the intersection of A and B. So what we have here is basically X over the probability of B is equal to, well, that's just the probability of A given that B happened, which is 0.45. And X, obviously, that's the intersection of the two events, which is 0.27. So 0.27 over P of B is equal to 0.45. And after this, it's pretty easy to solve for the actual value of PB. You should get that P of B is equal to, let's see, 3 over 5. Yes. So next part, we're going to find P of A. So the idea to find P of A here is to take P of A U B, this total block right here, like just the total Venn diagram, right? What we're going to do is we're going to add the intersection of B. And this is basically equal to event of A plus event of B. This is something you should definitely remember, this specific like law, because it's incredibly useful for problems where you have intersections or unions of different events. And basically the way you can kind of like conceptualize this is to just like draw it out on your Venn diagram. It's pretty easy to convince yourself of that fact. So what we're going to do here is we're just going to plug in the values, right? AUB, what is that? 0.78 plus A intersect B, that's 0.27. And that is equal to the probability of A plus the probability of B. And that is probability of A plus B, as we calculated before, 3 over 5, or equivalently in decimal form, 0.6. And basically what we get after this, I'll just clear this right part out for now. what we get for this one is that P of A is equal to 0.78 plus 0.27. That's 1.05 minus 0.6, so 0.45. P of A is equal to 0.45. Yeah, 45. 0.45. So now, last part, C. Show that events A prime and B are independent. So if A prime and B are independent, that would mean that P of A prime, let's see, P of A prime equals P of A prime given B. Wait, how do you do? Hold up. So we're actually gonna use the law at the very top again. So P of A. So two events are independent when this law holds true. So basically we're just gonna plug in A prime and B for this one times P of B. So we need to show that these two events are independent. So first of all, P of A prime, that's easy to find. It's just P of A, subtract that from 1, so 0.55. And then for P of B, as we've calculated earlier, it's 0.6. And then now, the probability of A prime union B, well, if you go back to our original Venn diagram, A, B, so the left circle denotes A, the right circle denotes B. P of A prime is really just everything except A. So all of the stuff I'm marking with blue right now is P of A. And then P of B is just this middle part. So actually, you can easily see that the union is just this little section over here. And the way to calculate that section is just to do P of B minus the intersection of A and B. Sorry. And P of B, as we've derived before, is 0.6. And A intersect B is 0.27. And plugging that in, we get this. And it's quite easy to confirm that this actually does hold true. So on to the next problem. This one is about mutually exclusive events, I believe. We're gonna give you around 5 minutes to practice with these two. Okay, welcome back. I hope you all had a chance to try this problem as well. So, for this one, two events A or B are such that these two quantities are equal to 0.3, and then A intersect B is equal to 0.2. So, the first thing we're going to do is draw out the Venn diagram for visualization. A and B. So first we're going to want to know like what all of these quantities mean in relation to the Venn diagram that we've just drawn. So A intersect B, that's just the probability of A and B both happening. So that would be the middle one here, 0.2. And P of A prime intersect B, well, that's just not A. So like everything that isn't A but is part of B, which is actually just this section right here. So that would be 0.3. And similarly for A intersect B prime, that's also 0.3. So now we're going to calculate the probability of A prime intersect B prime. So the idea here is it's hard to kind of like visualize what A prime and B prime look when they're like when you take the intersection of them. But if you draw out the Venn diagram, again, I'm just gonna do a different diagram because it's gonna get too messy. So not A is like everything that isn't A, highlighted in blue, and then not B is everything that is not part of B. And the picture I've drawn here is a little messy, but basically what you'll end up finding is that this is just equal to the probability that neither A or B happens. No A or B. And if we use our law that all of the probabilities in our sample space must add up to 1, then we have 0.3 plus 0.2 plus 0.3 plus this quantity that we want to find is equal to 1. And eventually what you find is that quantity is equal to 0.2. And that would be our answer for this one. A little bit too much arrows. So as a final statement, I'll just say P of A prime intersect B prime is equal to 0.2. And if you're actually doing this on an IB exam and this is like long answer, then you obviously don't want to do what I did over here, like writing a whole bunch of random stuff. You obviously want to assign variables, like don't just write a blank here. So if I were doing this on an actual IB exam, I'd start with stating like drawing out the picture and then stating like what each of these quantities mean. And then last part, what I'd do is I'd set a variable for this, let's say X, and then solve for X, and then I'd write down my solution. It's just that easy. So next part, calculate B prime. And the good part about, actually, before I proceed with the other problems, I'll just write down 0.2 on the outside as we've derived in part A. So now we're actually going to move on to part B. Part B is to calculate the complement of B or B prime. So the good thing about drawing a Venn diagram is that like you don't have to do any of the work associated with like just the algebra, because now you have the picture with you. You can see everything that's going on, and it's really, really easy to kind of like visualize what's actually happening. So notice that B prime is just everything that is not in B. And what's not in B? Well, we have this 0.3 over here. We have this 0.2 over here. Oh, guys. And adding those two together just gives us 0.5. little bit messy. It's fun. And that is our answer for part B. Basically, what I just did was I looked at my Venn diagram and then basically added up all the probabilities that I saw were not in event B. And that's just a really easy way to do it. And the last one is to find probability of A prime given B prime. And notice that with our previous formula, it's actually below here. So a quick way to evaluate conditional probabilities is to use this formula. And basically how we can do this is P of A prime intersect B prime over P of B. B prime. Because our two events are A prime and B prime. And basically, what we have to do here is we just have to evaluate these two terms, the numerator and the denominator. And the top term, we've actually already evaluated in part A to be 0.2. Now the bottom term, P of B prime, well, that's what we calculated in part B, 0.5. So actually, we've already done all of the work necessary to solve part C. And what we get is simply 2 over 5, or if you want to write it in decimal form, that's just 0.4. Next part, we're going to go on to conditional probability. And conditional probability is just what we've done before. P of A, given that B happened, is equal to the probability of A intersect B over probability of B. And this is almost guaranteed to show up on the exam. So you should probably review that, because conditional probability is one of those things that it's just really common. Now, I think that's all we have to discuss for probability. We do have an example problem, and I would like you to try it before I discuss it. So I'll give you 5 more minutes for that. Okay, guys, so it hasn't been 5 minutes yet, but we are on a time crunch, so I do have to get through this content real quick. If you'd like to keep trying the problem, just keep trying it, but I'll go over the solution right now. So, in a school, 60% of students take mathematics. Of those that take mathematics, 70% also take physics. And among students do not take mathematics, only 20% take physics. So, first thing to do here is translate all of this into words. So, first of all, 60% of students take math. That's just P of M is equal to 0.6 or 60%. Of those who take mathematics, 70% also take physics. So, the probability that a student takes physics, given that they take math, is equal to 0.7. And among the students who do not take mathematics, so given that they do not take mathematics, what is the probability that they take physics? Well, only 20%, so 0.2. And the first thing to do here is to calculate the probability of a student that takes physics, right? So first, probability of physics given that they take mathematics. Well, the probability that they take mathematics is 0.6. And we're going to multiply that by the probability that they take physics given mathematics, which is equal to 0.42, which is the probability, which is the total probability of people who do mathematics that also do physics. So P of M intersect M intersect P. So basically they both do mathematics and do math. And then the probability that they do physics given that they don't do mathematics, well, if they don't do mathematics, that's just 0.4 because they're not doing mathematics. The probability that they do mathematics is 0.6, so the probability that they don't do mathematics is 0.4, and then we're going to multiply that by this, which is 0.2, and we get 0.08. And that's that probability. So now we're going to draw out the Venn diagram as before, because it's really hard to visualize what these probabilities actually mean until you get a grasp for what they look like. So first of all, M intersect P, or like the probability that they do mathematics and physics here, is 0.42. And not math intersect physics over here is a probability that they don't do math but they do physics. So this is 0.08. And now let's see what other information that they give. So probability of mathematics is 0.6 in total. So we already have 0.42 that take both math and physics. So the ones that only take mathematics, that's just 0.6 minus 0.42 equals 0.18 over here. And now find the probability that a student takes both math and physics. Well, we've already done that. P of math intersect physics. That is just 0.42, which is the correct answer. And now for part B, given that the student takes physics, find the probability that they also take mathematics. And the idea here is we're going to write it first in probability notation. So given that they take physics, find the probability that they also take mathematics. So take math given that they take physics. Or using their notation is just M P. And that line just means given that they take physics. And as we've seen before, with conditional probability, when we have two events, we can simplify it as such. P of M intersect P over the probability of just P alone, or physics alone. And the probability of physics alone, what is that? Well, 0.42 plus 0.08, those are the two sections that are embedded in physics. Well, that's just 0.5. And then the top we have mathematics intersect physics. And mathematics intersect physics is just 0.42. And when we evaluate this, what we get is 0.84, which is the correct answer for part B. Okay. Next we have financial applications. So we'll give you guys a quick little break. 2 minutes. Yeah, sure. We'll give you a quick 2-minute little break before we start financial applications. Go drink some water. I don't know, do some push-ups.
Hello, so I'm Maggie. I'll be going over the financial application portion for the SL prep here. So first, let's go over compounding interest and effective rate. Like, even though interest is often given to you as an annual rate, it's not often compounded like that when you do mathematical questions. Oftentimes they'll just give you words like this, and it's very important that you know the definition of these words. For instance, annually obviously means once a year, but you also have semi-annually, which would be twice per year, and quarterly being 4 times a year. Things like monthly is like very obvious, that you have 12 times per year, but for weekly and daily, well, weekly is just 52 times, and bi-weekly being 26 times. So, and then for the daily, would be 365 times, and semi-monthly being 24 times. These are some very just often and common compounding frequencies, so it's good to have these memorized for when you do compounding interest problems. And then moving on to like the definition for periodic rate. To find the rate per period, all you really have to do is divide the annual rate by the number of periods per year. And you can often use this number when you make equations or formulas that will be coming up soon. And then for effective rate, this is the formula for an effective rate, where like R value here will be your annual interest rate, and N will be the number of compounding periods. And this is basically the formula that is used to derive other formulas, but we don't need to go too in depth about that right now. For instance, if you look at the effective rates for a 6% annual interest year, you can kind of generally see like how the effective rate is compounded with like the annually, semi-annually, etc., etc. And if you want to refer to this more, just take a look at the notes that we'll be putting on our link tree after the stream. And then moving on to the continuous growth. This is just a central idea behind the continuous growth for formula over here. So this is just limit. But then for the continuous growth formula, it's really in the form of y equals to ae to the power of r and t, where a is the initial value, r is your growth or decay rate, and t is the time in years. And we'll be coming back to something like this later. And then this will be like the rate table, which is deeply connected to the different compounding frequencies as above, and is basically an example of an application based on what we have before. So we'll be going on to the TVM solver for compound interest, which we should have done in math 20 and 30. And then if you don't remember, in both your Casio and TI-84, you can have these different ways of entering your TVM solver. If you don't remember, it's put up here, right over here. But then you'll be basically entered into a menu with different variable definitions. The first one being N, number of payments, and then I, annual interest rate. But please note that this is like in percentage already, so you don't have to convert it to a decimal before you put it into your menu. And then you have your present value, future value, the payment per period. It's very important when you do TVM values to know what your period is and like your compounding periods. And then you also have the payments per year and then the compounding periods per year. So you also really have to ensure when you do these questions to have the correct polarity, where if you cash it in, it'll be positive, but if you cash out, it's negative, because if you don't do the right polarity, you could make mistakes while doing it. And then for another definition is annuities, which are basically just like a series of equal payments at intervals. Like your present payment, your present value could just be like 0, or you could already have some present value. You just based on the question. And then let's do an example here. So Victor is planning to do some traveling. He'll be gone for 8 months and wants to withdraw $700 at the end of each month, starting 1 month after he leaves. His bank account earns 5.4% per year compounded monthly, and how much must Victor save in order to have the funds available for his trip? So all you need to do is to write down the variables that you have to start with, being payment, your interest rate, your present value, your future value, your payment per year, and your compounded per year. Because it says here that he'll be gone for 8 months, you start your number here will be 8 for 8 months. The payment you have will have to be 700, but it'll actually be negative 700 because you're withdrawing the 700. For your interests, since it says 5.4 but it's compounded monthly, it would be 5.4 divided by your 12 months to give you 0.45. And then the present value, because you're trying to withdraw this much money, this is actually what we'll be solving for. While your future value is going to be 0, because that's how much money you will build up towards after you withdraw all the money. For your payment per year, it'll be 12 and more 12 for compounding per year. And even though these two are the same for this question and are for a lot of different questions, these two values will not always be the same, so you have to keep an eye out for that. But if you plug this all into your calculator, it'll just automatically give you a number, and it'll be something for this question, 5455.01, and you just can refer back to the instructions as is on there. Okay, so we'll be moving on to exponential and logarithmic regression questions. The classic model for exponential growth or decays is just y equals to a times b to the power of x, or in some cases y equals to a times e to the power of rx. That's only for continuous change though, and in this case for this model, which will be your more common model, a will be your initial value, and if b is over 1, it'll indicate growth, but if it's like less than 1, it'll indicate decay, and obviously this b value can't be less than 0. And then we can do another example here involving goldfish, where the population of goldfish will decrease exponentially, so the size of the population, p after t days, is modeled by the function of p to t is equal to 8,000 times 2 to the negative t plus 100. To find for part A, to find the exact size of the initial population, all you really have to do is to plug in 0. So it'll literally just be p0 is equal to 8,000 times 2, 0 plus 100. And because this is just 1, it's just 8,100. And for B, if you're trying to find the size of the population after 5 days, you just replace t is equal to 5. So p to the 5 is equal to 8,000 times 2 to the negative 5 plus 100, which is just 350. And then for C, to calculate the time it takes for the size of the population to decrease to 120, all you have to do is to set P, T equals to 120 and then solve for T, so that 8,000 times 2 to the negative T plus 100 is equal to 120. If you just use your graphing calculator, you can get it so that T is equal to roughly 8.64 days. And then this part of the question over here is actually supposed to be used for D, but essentially the idea like a population will stabilize when it reaches the size of n, and you have to write down the n. You will actually be using the limits that was used above there, so that the limit of t going to infinity of pt will be equal to the limit of course, the other side of the equation, which would be 8,000 times 2 to the negative t plus 100. And obviously, oopsies, but if you have this value here, 2 to the negative t, as t goes into infinity, 2 to the negative t will just go to 0 as t goes into infinity. And obviously 100 will stay as 100, so it's just equal to 0 plus 100, which will be 100 fish as your starting n population. Okay, so moving on to logarithmic regression, which will be like used when the rate of increases slows over time. So you have like a diminishing return, for example. Your general equation for this regression will be y equals to a log x plus b. So our first example here, because it's a lot easier to illustrate this when you have an example, this following table here will show values of ln x and ln y, where the relationship between ln x and ln y can be modeled using a regression equation of ln y equals to a ln x plus b. To find the value of a and the value of b, all you need to do is just by using your graphing display calculator. If you enter for the Casio, if you enter the statistics menu and then press put in your data and press calc and then go into regression and then logarithmic regression, you'll be able to access this very easily, although the methods will be slightly different for a TI-84. But for this, you can just easily find that A will be roughly negative 0.564, while B will be roughly 4.74. This can be now used in part B, where you use the regression equation to estimate the value of y when x is equal to 4.12, because your equation here will just be y is equal to negative 0.564 ln x plus 4.74. By substituting in x is equal to 4.12, it's just y equals to negative 0.564 ln 4.12 plus 4.74. Now if you apply the ln to either side, you can just get that y is equal to e times negative 0.64 ln 4.12 plus 4.74. So y will just be roughly 51.5 if you plug that in properly. And then when you have, for part C of this question, because the relationship between x and y can be modeled using the formula y equals to p times x to the power of q, where p isn't 0 and q isn't 0 and q is also not equal to 1, the question asks to express ln y in terms of ln x and find the value of p and the value of q. So first, let's start with the equation that we already know, which is ln y equals to negative 0.564 ln x plus 4.74. So if you rewrite this equation using logarithmic laws, you can get that ln y is equal to ln x times to the power of 0.564 plus ln to e to the power of 4.74, which you can also use more logarithmic laws to just make it so that it's ln x 0.564 times e to the power of 4.74. So then y is just equal to x to the power of negative 0.564 times e to the power of 4.74. And therefore, by using your calculator to figure out the e value, it's really just y is equal to roughly 114 times x to the power of negative 0.564. So p will be roughly 114 here, while q will be roughly negative 0.564. And that can be your answer to the problem, and you can just square it off right there. Okay. So moving on to a logistic regression, which is used when like the growth has like an upper bound or a limiting value, usually for like population questions when you do it on the IB exam. The general formula for this is P is equal to C over 1 plus A times E to the power of negative Bn. So in this case, C over 1 plus A is just the initial value or the initial population, while C is like specifically the carrying capacity, so like the upper limit. And A and B are constants that are related to the growth rate and the shift, and N is just your time. And we can go over other questions later, but this is not a great example, so we're just going to be moving on from this for now. Okay, so now that you have these three models of exponential, logarithmic, and logistics, what model do you use? But to choose the right model, you often just have to see like what the question asks for. So for exponential, it tends to be used when you have like a consistent percent change, such as for like growth and decay. And logarithmic is just by the rapid change with slowing, so it's not a consistent percent change as an exponential, while logistic is used for when there's an upper limit and there's like a limited growth, such as like for populations. For instance, if your question here is a species of bird thought to be extinct was discovered on 14th March 1973, and then through careful protection and breeding, the population has continued to increase since then. And the Department of Conservative proposes that the population of birds T years after 14th March 1973 can be modeled by the function P of T is equal to 10 to the times e to the power of kt, where k is between 0 and 1 and t is bigger than 0, where on 14th of March 1993 the known population of birds was 50. So which model would you use and how would you do it? So I'll be giving you guys 5 minutes to look through this question. Okay, so we'll be going back to get the answer to this question now. So for part A, where it's use the model to estimate the population of birds on 14th of March for 2023, well, you know that because it starts on 1973, because you have 1993 minus 1973, which will give you 20. So then for the first part, because we know that on 14th of March 1993, the known population of birds was 50. So the population, when it's of 20, because 20 is the number of years after the 1973, this is just equal to 50. So therefore, 50 is equal to 10 times e to the 20k. So then here we'll be looking for the k value, so we can have a further equation to estimate the population of birds for 2023. So because of this, e to the power of 20k is just equal to 5. So by your graphing display calculator, the k value should be roughly 0.08047. Now, because of that, we can have our bigger equation to estimate the population of birds for the year for 2023. So pt is just equal to 10 times e to the power of 0.08047t. Now, because 2023 minus 1973 is equal to 50 years, you plug in t equals to 50, which will give you 10 times e to the power of 0.08047 times 50. So therefore, p of 50 is just roughly 559 for the population of birds at this time. And then for the second part of this question, where the known population of birds on the 14th of March 2023 was 502, and a new model is proposed in which the population on March 14th, 1973 was 10, population on the same day was 502, and the population increased at a constant r% per year, where you have to find the value of r. Actually, for this question, instead of using a regression, you can actually just use a compound interest equation to solve it, because we have a constant rate per year. So we can use the equation, which this one isn't one that we have particularly learned, but it's good to keep this one in mind for now. So for instance, the compounding interest equation is future value is equal to present value times 1 plus r over 100k to the power of k and n. Okay, so because we know here that our future value has to be 502 because it happens in 2023, and our present value is 10 because it happened in 1973, your k value is 1 because it's a constant rate, and then the n is just equal to 50 right now, because we know that the known population was 50 in 1993. So just to plug everything in, 502 is equal to 10 times 1 plus r over 100, because k is just equal to 1 to the power of 50. And by doing this, we can solve for r, which will be your constant rate of change per year. If you just plug this into your graphing display calculator, you can solve it so that r is just equal to 8.15, which should be your answer for this question. And even though this equation isn't like explicitly talked about, it's just a good one to keep in mind to solve this kind of questions, especially if you know there's a constant rate of change for a year. Okay, so for now we'll be going on a 10-minute break before we come back to talk about coordinate geometry. So go take a rest, guys.
Alright, so the next section will be coordinate geometry. Coordinate geometry, well, the most basic thing that we have to figure out is equations of a line. There's actually one equation missing here, but I'll get into that in a second. The first one is the most basic equation of a line that we usually cover, and that is y equals mx plus b right here. You should probably know this if you're about to take the IB exam, but the m is the slope, right? So if m is positive, then the line goes like this, and if m is negative, then like the line goes like that, and so on. And then b is the y-intercept, so where it crosses the y-axis. So if b is positive, it's in this region. If b is negative, it's in this region. If b is 0, it goes through the origin, etc., etc. It's just all like routine stuff, right? Standard form is like the really bad form that they force you to like convert your answer into afterward. So for example, if we have y equals 3 over 2x minus 4, we want to make all of these into integers first, so we multiply both sides by 2 to get 2y equals 3x minus 8. And we move everything to one side. You get 3x minus 2y minus 8 equals 0. And usually on tests, they will specify a is greater than 0, so that there are not two possible answers. Like here, you can have negative 3x plus 2y plus 8 equals 0 as an answer as well. And usually they will specify a, b, and c are integers. The third one is point slope form. This one is really useful for when you have one point that you know the line goes through and the slope of the line. So I'll just draw a little illustration of that. So if the point is QP, questionable choice, and we know that M is the slope of the line, so let's say the line goes like this, then we know that if we have any point here, let's call this xy, right? The slope between xy and qp can be written as y minus p over x minus q, because this is delta y over delta x, right? And we know that slope equals m, so multiplying both sides by x minus q, we get y minus p equals m times x minus q, which is the desired form. And the last one that's actually missing from here is two-point form. Two-point form is very similar to this, but we don't know m. Instead, we know 2 points on a line, as the name suggests. So I'll draw the Cartesian grid again. Let's say this point is x1, y1, and these x values are fixed, so these are not variables. And we have x2, y2 here. Well, we can use a similar strategy as the two-point form. We can use a similar strategy as the point slope form, but now we can calculate the slope explicitly as y2 minus y1 over x2 minus x1, right? And I'll leave it as an exercise to prove that this is equal to y1 minus y2, etc. And because we know this form, and we know that arbitrary point on the line, x, y, the slope between, let's call this fixed point a1, this point a2, and this point p. We know that the slope between p and a1 has to be the same as the slope between a2 and a1. So we get this is equal to y minus y1 over x minus x1. And because we don't want an NPV on the denominator here, then we multiply both sides by x minus x1 to get y2 minus y1 over x2 minus x1 times x minus x1 equals y minus y1. And this here is called two-point form, as I said. I'll declutter a little bit by erasing the and I've already covered this a little bit. The slope of a line, because 2 points determine a line uniquely, the slope of a line is change in y over change in x, which is y2 minus y1 over x2 minus x1. Make sure not to make a mistake such as writing y2 minus y1 over x1 minus x2. You have to always take the coordinate from a2 and then subtract the coordinate from a1, or you can do it the other way around. So obviously we have y1 minus y2 over x1 minus x2 is equal to this thing, because both of these signs are just flipped. But if you only flip one, this is actually equal to negative of the original slope. So you're cooked if you use this strategy. So don't do that. Y-intercept is the value of y when x is equal to 0. And so you can see that if we have the original y equals mx plus b, if you set x equal to 0, then the mx term dies. Then y equals b. This b is the y-intercept. And the x-intercept is the value of x when y equals 0. Because obviously this is some fundamental things, but on any point on the x-axis here, you have y equals 0, and on any point on the y-axis here, you have x equals 0, right? So let's say we have y equals mx plus b, and we want to find a y-intercept. So we have 0 equals mx plus b, and then we get negative b over m equals x, and this over here is the x-intercept. So on this graph, it will be this point right here. The distance between 2 points on the plane is easy to calculate just by using the Pythagorean theorem. So what we can do is, if we have this point A1 here and this point A2 here, we can calculate this. We'll call this delta x, and we'll call this, this should be delta y. This is delta x, and if we use Pythagorean theorem, we find that d equals square root of delta x squared plus delta y squared. And delta x obviously equals x2 minus x1 by definition, and delta y equals y2 minus y1 by definition as well. So then we get this formula. So it is equal to x2 minus x1 squared plus y2 minus y1 squared. And here, if you make this mistake here, it actually doesn't matter, because the squaring gets rid of the sign. Like, for example, negative 28 squared equals 6, 7. Okay, terrible example. Negative 27 squared equals 729, and so does 27 squared, right? So, yeah. Anyways, on the IB exam, you do have to know this for 3 dimensions, and the way we show that is you pick 2 points. A1 will be on like some plane, and A2 will be on like some point that's not necessarily on the same plane, right? If we project A2 onto this like flat plane, then this distance here is d. This distance here is delta z, right? So we use Pythagorean theorem. We'll call this d prime, because this is not actually the d we're trying to find. This is d. So we have d squared equals d dash squared plus delta z squared. And if we have this, I'll erase our derivation for the 2d case. We know that d dash, because it's 2d, that d dash equals d dash squared is, we removed the square root, is x2 minus x1 squared plus y2 minus y1 squared. And delta z by definition equals z2 minus z1. So delta z squared equals z2 minus z1 squared. And I should probably have brackets here, because the delta z should be one variable. So then we have d squared equals square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And for example, using this result, we can find that the distance between 2 opposite vertices of a cube is square root of a unit cube is square root 3, and we get that by noting that this distance, and this distance are all 1. So then we get square root 1 squared plus 1 squared plus 1 squared equals square root 3. And if we draw the rest of the cube here, then like you have this, and the distance between this and this is root 3. And to illustrate our proof here, notice that the diagonal here has length square root 2, and because this line here is orthogonal to the plane, then these two lines are also perpendicular, and then we can apply Pythagorean theorem again, and then we can notice that this length is root 3. the midpoint of 2 points has this formula here, and we can do that by drawing something called the medial triangle. So let me erase this. All right, so we take right triangle, because in Cartesian coordinates it's always better to have a right triangle, right? We'll call this A2, call this A1, and the midpoint bisects this side, right? So we construct the point that bisects. I'll call this point B, because why not? We'll draw the midpoint of A2B. We'll draw the midpoint of A1B. And we notice that after we draw these, we notice we have a lot of pairs of similar triangles, because these are parallel and these are parallel, trivially, because there's a lot of right angles here, right? And anyways, we find that the ratio of this here to this is 1 to 2. So we have A1B is equal to delta x, right? And because the ratio of this to the whole thing is 1 to 2, this is delta x over 2, and this thing is delta y over 2 by a similar logic. And we can compute explicitly that delta x equals x2 over minus x1. So half of delta x equals x2 minus x1 over 2. And then we have x1, which is the x coordinate of a1, plus 1 half delta x, which is x2 minus x1 over 2, is equal to x2 minus x1 plus 2x1 all over 2, which is equal to x1 plus x2 over 2. And we can apply the same reasoning to the y-axis, so that this thing is delta y here, and then this thing is 1 half delta y. So then we have x1 plus x2 over 2, y1 plus y2 over 2 as the midpoint of these two segments. And of course, this generalizes to 3D as well. So if you want to find the midpoint between, let's say 0, 0, 0 and 1, 3, 5, for example, then you take the average of these two, which is 1 half, the average of 0 and 3, which is 3 over 2, and the average of 0 and 5, which is 5 over 2. And this is the midpoint of those two segments in the midpoint of the segment formed by these 2 points in 3-dimensional space. So yeah, we have that. Parallel lines have the same slope. I think this is pretty self-explanatory, because parallel lines have no intersections, right? So let's say I were to solve y equals mx plus b1 and y equals mx plus b2. Substitute, we can subtract these two equations. The y and mx both die, so we have 0, we have like b2 equals b1, and if b1 was like 1 and b2 was like pi, then this will have no solution, right? So that's why they're parallel. And perpendicular lines, the product of their slopes is -1, and I don't think this is very difficult to show. I think this requires some trick to show it. Alright, whatever. Proof is left is an exercise for the reader, I guess. Okay. Collinear points, they share the same line by definition. So the 3 points have the same. You have this. Let's say 3 points A, B, and C are collinear. Then the slope of AB, BC, and CA are all. I mean, not CA because slope is signed. And AC should all be the same. So if we go back to where we derived 2-point form, the slope between A1 and A2, A1 and P and A2 are both equal to this value M, which is delta y over delta x, right? So that's how you can show a few points are collinear. For example, if we have 2, 3, 4, 5, and 6, 7, we can check that the delta x between these 2 points is 2, and delta y is also 2. So the slope between these points is 1. You can similarly check that these two, the slope between these two are also 1, and the slope between this and this is 4 over 4, which equals 1. And these 3 points are collinear. But if this 7 was changed to an 8, for example, the slope between these 2 points would be 1. The slope between these 2 points would actually be 3 over 2. So then these points look something like this, right? So then they're not collinear. Lines that intersect at a given point. So usually you have to solve system of equations. There's a shortcut called Cramer's rule, which I'm not going to get into here. But if you want to use Gaussian substitution, that's fine as well. I'll just give a quick example. Let's say we have 2 lines that are given to us in different forms because the test sucks, right? So the first line will be given in slope-intercept. So let's say we have y equals 2x minus 3 is our first line. And the second line will be given to us in general form. So let's say we have 3y minus 2x plus 5 equals 0. And to solve a system of equations, usually you want to like kill one of the variables, right? So what we can do here is we rewrite the first equation. Here you see that we have a 2x term here and a 2x term here. So if you can add the 2 equations somehow, that would be pretty good. So we rewrite the first equation so that 2x minus 3 is on this side. We have 2x minus 3 equals y. Okay, I should probably not put the 1 there. And after adding these 2 equations, the 2 x's get cancelled out. We have 3y plus 2 equals y, or 2y equals negative 2, or y equals negative 1, right? And after we find y equals negative 1, we can plug it back in this equation. We get negative 1 equals 2x minus 3, or 2 equals 2x, or 1 equals x. And it's not hard to check that 1, negative 1 lies on both lines. And sometimes when the system of equations is bad, you will get either no solution or infinitely many solutions. And I'll illustrate graphically what those examples look like. So let's say we have this fixed black line over here. An arbitrary line would usually have one solution. I mean, one intersection with this line. So this blue line here only has one intersection, right? We also have 0 intersections. So I'll draw this red line here, and it will be parallel to the black line. So the red line and the black line never intersect by definition of the parallel lines, right? And the 2 lines can actually coincide if the 2 equations are like the same line, but just written in different form. So, for example, if we have the equation y equals x, we can actually write this in slope-intercept form. So, for example, y equals x goes through the point pi and pi, right? So, and the slope is obviously equal to 1. So if we use slope-intercept form here, we use point-slope form here, we get y minus pi equals 1 times x minus pi. And obviously you can trivially see that the 1 does nothing and the negative pi's get cancelled out. But when the values are slightly different, it might be a bit harder to see. But if you ever end up with a step like x equals x at the end of your simplification, then you know the 2 lines actually coincide, and the system of equations is bad. Perpendicular bisector. This is useful for Voronoi diagrams, but it's like also useful for a bunch of other stuff. For example, from circle geometry, you might remember that if you have a chord in a circle and a line that goes through the midpoint of the chord and the center of the circle, then that's actually a perpendicular bisector of the chord. Sometimes it's useful for like those word problems that you have to find depth or something, right? Anyways, a perpendicular bisector looks like this. You have A, you have B, you have the midpoint, which I'm going to denote M, and a line here that goes through them. So from what we have learned before, we know that we'll call this line here. This shouldn't be okay. Yeah. Call this this segment. Okay, we can just call it AB, but this line we can call L, right? We know that the slope of L times the slope of AB equals -1 because they're perpendicular, right? And we also know that this line L includes the midpoint M. So we know that M, M, which is, we'll call A like ax, ay, this bx, by. We know the m, which is ax plus bx over 2, ay plus by over 2, lies on this line. So rearranging this, we just move the slope of AB, which is like very easy to find over here. We know the slope of the line L. We also know a point that goes through it. So if we use point slope form, we can pretty easily find the thing, the equation of L. And after we find the equation of L, it's easy to do a bunch of other stuff with it. Another cool property about the perpendicular bisector is that any point on the perpendicular bisector, let's call this point P, the distance of PB and PA are actually the same. And this is very easy to prove because AM and BM are the same. MP is obviously the same as itself. So if we apply Pythagorean theorem on this triangle MBP over here and this triangle MPA over here, then you get AP is equal to this distance plus squared plus this distance squared. I mean AP squared, and BP squared equals this distance squared plus this distance squared here. They're obviously the same. So then we're done. And we'll do some example problems, I guess. The first example, we're given 2 points, and we're going to find the length of the line segment. So the length of the line segment is the same as the distance between the 2 points, right? And we know that the distance formula is just d equals square root of x2 minus x1 squared plus y2 minus y1 squared. And I think the only difficult part about this problem is making sure you don't mess up on the signs, which is really easy to do. This is just straight substitution at this point. Negative 2 minus 1 squared plus 6 minus negative 3 squared. And this is equal to negative 3 squared is 9 plus 6 minus negative 3 is 9. 9 squared. And here you can take out 9, which is 3 squared, from the radical. So we get 3 times 1 plus 9, which is equal to 3 root 10. And this is your answer. As I said, these signs here, if you're not sure that you can not mess up, which I've done on so many tests, add brackets around negative 3 so you don't forget something. Anyways, next example. The line L1 shown here has the equation 2x plus 3y equals 26. So this looks the closest to the standard form that we talked about, right? And the line L2 passes through the origin O, which means the origin is obviously 0, 0, right? And it's perpendicular to L1. So if we can compute the slope of L1, then we know that the slope of this has been a negative reciprocal of the slope of L1, and we also have a point on this line, so we can use point slope form. You can also notice that any line that goes through the origin has to be in the form y equals mx because the y-intercept is at 0, right? There's also a third way to do this, which I might show you in a bit, but let's do the standard strategy first. So to find the slope, we have to rearrange this equation here into y equals mx plus b, right? So let's first isolate y. We get 3y equals negative 2x plus 26. Y equals negative 2 over 3. X plus 26 over 3. Unfortunately, 26 is 2 times 13, and 13 is prime, so we can't simplify anything else. So the slope here is negative 2 over 3. The negative reciprocal of that is 3 over 2. So we know that this line L2, or OC as we see here, has slope 3 over 2. And we can substitute into point slope form. But as I said, y equals mx plus b is the general equation of a line. But we know that the y-intercept equals 0. So this term is gone. And we have y equals mx as the equation of this line. But we know m is equal to 3 over 2. So y equals 3 over 2x is the answer to this question. And the line L2 intersects the line L1 at the point C. Line L1 crosses the y-axis at the point B as shown in figure 2. find the area of triangle OBC. So the question gives these two lines as perpendicular. So if we want to solve this question using brute force, what we can do is compute OC, compute BC. So first we have to compute the coordinates of C and B, but B is easy to do because we have the equation for the line already, and C is not hard to do either because we have the equation for both the line the line L2 and the line L1, and we have to find the intersection by solving a system of equations as we covered before, right? And after we compute OC using the Pythagorean theorem and BC using the Pythagorean theorem again, we can just use the area of the triangle is equal to 1/2 times the distance of OC times the distance of BC, and this should give us the area. This is going to be a pretty brutal computation, and I'm probably going to make a bunch of trivial mistakes as I usually do, but I'll try to walk through it. And after this, I'll show you a much better way of solving this problem because this method is like kind of bad. Alright, first we compute C. We have 2x plus 3y equals 26, and I unfortunately erased it here, but y equals, what is this pen? Yeah, this line L2 is actually y equals 3 over 2x. And we have 2x plus 3y equals 36. We want to solve this equation. But the good thing is we already have y equals a function of x. We can immediately substitute into here. We get 2x plus 9 over 2x equals 26. And we notice that the numerator of this thing is 13, right? We have 13 over 2x equals 26. That's pretty good because we get rid of the bad prime in 13 and 26. So then we get x equals 4 for this point C. So it's something 4. But remember how, oh wait, what? 4 is the x-intercept, the x coordinate, not the y coordinate. And we know that y equals 3 over 2x, right? So it equals 3 over 2 times 4, which equals 6. So 4, 6 is the point here, is the point C. And now let's compute B. We can actually do this step separately because it doesn't depend on the answer to the previous step. So you can compute B and C in whichever order you like. B is the y-intercept, right? So the y-intercept by definition is when x equals 0. So we get 2x plus 3y equals 26. And because x equals 0, we just get 3y equals 26 and y equals 26 over 3. And actually, before when we solved the, did I erase it? Okay, yeah, we unfortunately erased this, but when we turned this into point slope form, we could have read this like from the equation, but I didn't see this question. So anyways, this is 0, 26 over 3. And yeah, the computations from here are not going to be very good. Alright, so O is 0, 0, right? So if O is 0, 0 and this point is 4, 6, then it's not hard to see that this length here is 4, that this length here is 6, and this is a 2, 3 root 13 triangle, but it's scaled out by a factor of 2. So this distance here is 2 root 13, which, looking at it right now, it looks like we're cooked, right? Because this form is a rational number, and we have 2 root 13 as one of the things. So if we do not get another factor of root 13 in BC, we know we did something wrong. And honestly, I probably did, but let's check from here. So we have this triangle here. Oh, what is that? Is a terrible line. Here we have B, here we have C, and 6 is 18 over 3, I think. What? So again, if we were to draw this line, we can find that the change in x is 4 again, and the change in y is negative 8 over 3. But because we're doing distances here, we can just do 8 over 3. And 4 is equal to 12 over 3, right? So we can see, again, this is a 2, 3, root 13 triangle. But the sides are scaled by a factor of 4 over... Yeah, they're scaled by a factor of 4 over 3, I think. Yeah, because 2 times 4 over 3 equals 8 over 3, and 3 times 4 over 3 equals 12 over 3, or 4. But if you don't recognize this, you can use Pythagorean theorem to compute it, and you'll get the same answer. So, because we scaled this triangle up by a factor of 4 over 3, then this side would be root 13 times 4 over 3, right? And of course, we got that root 13 factor that we were looking for, so we know we might not be that cooked after all. So as I said here, we can compute the area of this red section now. What? Okay, so area of the triangle equals 1/2 OC times BC. Again, remember there's a right angle, so we can just use 1/2 base times height, which equals 1/2 times 2 root 13 times 4 over 3 root 13, and the 1/2 and 2 cancel. Square root 13 times square root 13 is 13 by definition, so it's equal to 13 times 4 over 3, which equals 52 over 3, I think. And I think that is your answer. But again, with this kind of question, it's pretty tedious. It's pretty easy to get wrong. So make sure you write out all your steps. Don't be like me and be very disorganized. And on the exam, make sure you write out your steps carefully so you don't make small sign errors and things, because even one sign error will kill your progress for this problem. And there's actually another solution using similar triangles, which I'll leave as a I'll leave as an exercise to the viewer here to figure out what to do. But a hint is, if you compute OB and you compute this point, which I'll call D here, you notice that OBC is actually similar to OBC is similar to DBL, and using those ratios, you can come up with a ratio for the area. And now I have Voronoi diagrams, which is probably the worst topic in here. So basically, the strategy is you want to draw the perpendicular bisector between each pair of points. So if you have this point here and this point here, as I said, if you're on the perpendicular bisector, you have the same distance between these. This is not hard to check using Pythagorean theorem. And if you're on this side of the point, I'll use a different color. If you're on this side of the point, then you make a projection onto, on this side of the bisector, and you make a projection onto the bisector. You notice that the change in y is actually the same. But if you're on this side, by definition, the change in x to this point here is greater than the change in x here, so you're closer to this point. Alright, so the question says that there's an ambulance at 2,5, and 2,5 is this point, so it's actually on the perpendicular bisector. And determine which hospitals the ambulance should go. Well, it's on the border between these two regions, and if you want to think about it the other way, it's on the perpendicular bisector of this point and this point, right? So either of them can work. And to determine the distance, the graph paper really helps, because either you can measure it with a ruler and see it's 2.26 and then conclude it's root 5, or actually I don't recommend doing that, but whatever. Or you can notice this is 1, this is 2, and by Pythagorean theorem the distance is root 5, and this, you have the exact same triangle, just oriented differently. And we should probably label the hospitals, because that's what the question says to do. 3,3 is here, 7,3 is here, 4,6 is here. I don't know why they didn't give it in like counterclockwise order at least, but D is here. So then the distance is root 5, and notice they gave 1 unit represents 1 kilometer. So then using the distance formula, we find that root 5 kilometers, or if we were to use a calculator, I think it's root 6. I mean 2.26. Oh, it's 2.236, whatever. So it's approximately 2.24 kilometers. And alright, the next question is that you want to find a point that's equidistant, so same distance from points B and C, right? And you notice here there's actually multiple solutions, but having a lattice point is obviously the best. By inspection, you can notice that this line here is the perpendicular bisector. So this point is like the only lattice point we have on the diagram that's actually on this bisector here. So the coordinates of this point is 5, 4. Wait, it never actually explicitly says where the lattice, it has to be a lattice point. Technically every point on this line works, and it's not hard to prove there's infinitely many lattice points that satisfy this. And of course, to construct the equation of a perpendicular bisector, you can use the same strategy as we did before. Compute the midpoint, compute the slope of BC, compute the slope that you need, and then use point slope form to solve the problem. Apparently that's it for this part. I do have a cool application of this I want to present, but I'm not sure if we have time, so
Okay, hello. So we're gonna move on to the next section, which is binomial theorem and expansion. So for all of us at Western, when we took Math 30, this is probably just a review. So for Pascal's triangle, if you don't remember, it looks like this. It's like a triangle. And basically, you start from 1, and then like every single number at the edge is also a 1. And then everything that's like not a 1, you get it by like adding the 2 numbers that are directly above. So if you look at this 2, like right here, 2 is like 1 plus 1, right? So that's how the Pascal's triangle works. And then the binomial theorem is essentially saying that when you have like a plus b and then you raise that to the power of n, essentially the coefficients is going to be whatever is in that specific nth row of the Pascal's triangle. Okay, so if you see this like 1, 3, 3, 1 row right here, like this row right here, that's equal to, hold on, a plus b, and you raise that to the power of 3, and then you're going to get the coefficients of 1 like something plus 3 something plus 3 something plus 1 something. Okay, so that's how it works. Now in terms of like the terminology you need to know, n, so n right here is going to be the degree of the expansion. So when we have a plus b to the power of n, this n is going to be the degree right here. This is degree. Okay, And then k is essentially just like a variable we define. This, by the way, right here is a sigma symbol, so it means like you add everything from 0 to n. Okay, and then n choose k, as you know, is n factorial over k factorial times n minus k factorial. If you don't know how to do this, your calculator should be able to compute this. And then, of course, this term right here is called the binomial coefficient. Okay, so this thing right here. And then each term is of the form n choose k times a to the power of n minus k times b to the k. So this is kind of something you just need to look on the formula sheet, or you kind of just need to like know in your head. So basically, if it says like the fifth term, you just have to remember that like you have to do n minus, let's say 5, and then b to the 5. So that's how it works. Okay, so let's look at a quick example. So it asks us to consider the expansion of 3x plus p over x raised to the power of 8, where p is greater than 0. So it also gives us that the coefficient of the term in x to the power of 4 is equal to the coefficient of the term in x to the power of 6. Now it tells us to find this particular value of p. Okay, cool. So how you approach this question is you try to look at the information you're given and then like write that in terms of math. Okay, so that's basically how you solve every single word problem. So if you look at this, if we apply the binomial theorem, so I'm just going to write it here for easier reference. It's a plus b to the power of n, okay, equals sum from k equals 0 to n, and then now you're going to do the binomial coefficient like so, and then now you're going to place the actual term of what you're trying to do. So you're going to take the first chunk right here, okay, raise that to the power of n minus k. You take the second chunk right here and then do b to the power of k. So this is the formula that we're essentially getting. Now if it tells us to look for the term that's x to the power of 4, let's say like we can just let k1 be the term of the expansion so that we have this x4 component of it. So let k1 be let k1 be the term where, and then you would probably just write the whole thing out. There's like not really much space here, so you would let k1 etc. Okay, and then you would do, so n here is equal to 8, so you're going to do 8 choose k1, and then times, now the a here is 3x, okay, and then now you're going to write that in terms of the formula, and you're going to put the second term here, which is p over x raised to the power of k. Alright, now we're only looking for like the specific value of x, like the exponent raised of it. So here you can see that if you take all of like these coefficients out, we get that x to the power of, so right here, x to the power of 8 minus k, okay, times, and then 1 over x to the power of k, okay, and then we can simplify this to x 8 minus k, and then this would, like this exponent right here would be turned to negative. So 8 minus 2k equals x to the 4. So 8 minus 2k, just like so, is equal to 4, and k1 equals 2. And then we can actually just rinse and repeat, because you can just replace this with like a second term. So let's say x to the 8 minus k2 equals x to the 6. So then you get k2 equals 1, okay? And then now you just have to plug both of these in back into like this block right here, and then you would get the coefficient and you set them equal and you solve for p. So just like for ease of space, I'm going to zoom in a little bit. We have 8, let's start with p1, so 8 choose 2 times, and then now we already know like the term is going to be x to the 4, so we can only look at the numbers now. So 3 to the power of 8 minus 2 is 6, times now p to the power of k, so p to the power of 2 equals 8 choose 1, 3 to the 7 times p, just like so. And now you plug this all into your calculator, we can notice like p equals all of this right here divided by all of this. So fortunately 8 times 3 to the 7 divided by, and then 8 choose 2 is going to be 28 times 3 to the 6, and I think we get the value of 6/7. Hopefully that's correct. So we're going to box our answer, and this is going to be the solution to the problem. So I'm just going to like really quickly recap that. Essentially what we just did was we took all the given information, so we represented the term that had that had the x to the power of 4, just like so, like this chunk right here. And then we took out every single value of x, and then like we looked at the exponents, and then you can see that x to the power of 8 minus 2k equals x to the 4. Solve for that value of k, and the same thing for x to the 6. And then you set the coefficients equal and you solve for p. So essentially, the master tip I can give you is just write everything in terms of math and then solve for whatever you need to find. Okay, so there's also a second practice problem. And honestly, like if I had this on the SL test, I would probably just do sum of cubes because that would be a lot easier. Or even just like the most straightforward way to do this is just expand everything you see. But you can also do this in terms of binomial expansion, which can make your work easier. So if you recall, a plus b to the power of 3 equals, and then by the binomial expansion we have we're going to put the coefficients down. So 1, 3, 3, 1. 1, 3, 3, 1, like that. And if you recall from the formula, we have a to the power of 3 right here, a squared b, ab, and then b cubed, like that. Okay, and then essentially you just want to do the same thing, but then replace it with these numbers up here. So we have for the first one we have a equals 2n, and this is b, this is a, this is b. So we have 2 n minus 1 cubed plus 2n plus 1 cubed becomes, and then we're going to write essentially the 1 3 3 1 out. So 1 3 3 1, and then times 2n cubed plus, and this would be 2n squared times -1 plus 3 times, okay, this is actually not going to work out. So essentially we just want to keep the 1 3 3 1 coefficients in mind, and we're going to do 2n cubed plus 2n squared times -1 times 3, that's our coefficients, plus 2n times -1 squared times 3, and then plus at the very end -1 cubed. Okay, and then you would do the same thing but for the opposite sign, so 2n cubed, just like so. Okay, and you notice that basically all of these cancel out. Oh, never mind. So that cancels out. This cancels out. Oh my. Okay, and then what you're left with are these terms. So this equals 16 and cubed, and then plus here becomes 6 times 2 is 12. So plus 12n, and we're done, because we've shown that the left side equals right side. Okay, now here it asks us to do hence or otherwise. So if you see this term, hence or otherwise, it just means, it basically means nothing, because it's like you can, what it means is you can use the thing from the previous problem to help you, or you cannot. So like it actually does not matter. So basically it says prove the sum of the cubes of any two consecutive odd integers is divisible by 4. So if we look at the previous problem, it was basically saying 2n minus 1 cubed and 2n plus 1 cubed. Okay, 2n is an even number, you subtract 1, it's going to be odd, right? So that chunk inside is going to be odd. And then right here, you can apply the same logic. This thing is even, this thing is odd, so the entire thing has to be odd, okay? And then so here you already have this odd integer cubed plus another odd integer cubed that happens to be consecutive because like, well, like let's say this is like 5, that has to be 7, right? And then this has to be divisible by 4. So essentially, we see that this is like, this by itself by definition is like one odd integer. This one is like the next consecutive one. And then now we just have to prove it is divisible by 4. So if we, as we showed with like the previous part, it was equal to 16n cubed plus 12n, right? So let's say we wrote that entire expression out without all this like even odd stuff, and we just wrote 16n cubed plus 12n. Now, if it asks if it's divisible by 4, maybe you can try factoring out the 4. And then you see that the inside is also an integer because like we know that n belongs to a set of integers, and then obviously 4n cubed plus 3n also has to be part of a set of integers. And so this thing right here must be like divisible by 4 because you could take the factor of 4 out. And then if you were to write this like on the SL exam, I would probably just do therefore this thing is like, so 4 divides, this is the divide symbol, it's like a vertical line, and then the term on the left, okay, and then we are done. So that's essentially the gist of binomial expansion. If it ever asks you to prove like any statement and says hence or otherwise, just basically ignore the hence or otherwise. Okay, we're going to move on quickly to binomial probability. So in terms of terminology, first off, we have the number of trials, which is n, okay? And then binomial means you either like win or you lose. So it's like a 1 or a 0. That's why it's called binomial, because like 2. And then probability of success is here, it says it's constant. So that means that like, let's say you're rolling a dice, the dice is not going to like suddenly increase the number of faces or something. You're still using the same dice, okay? And then trials are independent, which means that like if you flip a coin, it's not going to affect the second time you flip the same coin, okay? So the formula that we looked like earlier, this kind of resembles the binomial theorem. And essentially here it's asking like, the way this is different is, let's say we're doing a specific number of trials, which is n, and then like let's say we flip a coin, but then it has like a 5% chance of landing on its head for some reason, okay? So then like here in this example problem, we see kind of like a similar thing. So we're trying to hit a target with probability of success is 0.05, and then she tries to hit it 10 times, and then like the problems you'll usually get is like, what's the chance she's going to be extremely lucky and she hits it like 5 times, for example, okay? So honestly, let's just go straight into the problem. We have Abby hits a target with probability 0.05, she hits it 10 times. So I'm going to show you 2 ways to do this problem, okay? One way is you completely forget how to use your calculator, and second way is you remember how to use your calculator, okay? So with your calculator, if we look at this statement right here, we can write this in terms of the probability function x is modeled by the binomial distribution with 10 trials with probability 0.05 of success, okay? And then now you're going to use your calculator. Now I know on the TI-84, if it says like hits the specific target exactly 0 times, you would use the binomial PDF probability density function command, because you're only doing one specific value, okay? So then you're going to do binom PDF, and then 10, 0.05, 1, solve that in your calculator. And then hopefully, so I'll go second distribution, I would scroll to the bottom. We see binomial PDF, trials is 10, 0.05. And then we get the value of, oh, wait a minute, this says target 0 times, my bad. So you would actually do the same thing but with 0. Get like just about 60%. Now, usually you would write this in terms of 3 significant digits, so this would be 0.599. Great. And then if you do the same thing, but then like you forgot to use your calculator, what you can do is just think about this like mathematically. So if she hits the target 0 times, that means she fails 10 times. So that's like pretty horrible. You just do 0.95, raise that to the power of 10. You also get 0.599. Okay. Now, what's the probability that she hits the target exactly 3 times? So this is kind of like the similar thing. Again, there's 2 ways to do it. One is if you're like you wake up day of exam and you completely forget how to do things. It's going to be, so if you use your calculator, same thing. It's going to be multiplied by binomial distribution of 10 trials, and then 0.05 is the chance. Now you're going to use binom PDF, just like so, and then of 3. And then I'm going to plug that into my calculator, get 0.0105. So pretty unlikely. And then if you forget how to use your calculator, now you can just use the binomial theorem. So essentially, if it's saying exactly 3 times, we do 10, choose 3 times, and then you do the chance of success 3 times, and chance of failure, and then 10 minus 3, which is 7 times. That's like the remaining amounts. You should also get the same number as well. Okay, nice. Now, what is the probability that she hits the target 3 times or fewer? And then the time-saving way you can do this is, again, it models the same function like so, and then instead of binom PDF, you use binom CDF, which is like cumulative. So this essentially takes all the binomial PDF functions and it calculates it for 0, 1, 2, and 3. So every integer less than that. Okay, and then you just go like so, and then if I calculate it in the calculator, I get 99, okay, well, essentially 0.999, so extremely likely. Okay, so, oh boy. And then if like you do this traditionally mathematically, we essentially repeat this process for k equals 0, 1, 2, and 3, and then add. So that's obviously like a lot more tedious, so just use your calculator for these types of questions. Great. So just like a really quick recap, binomial PDF is when you want to find like a really exact, precise value, like the chance of getting exactly this amount of successes. And then binomial CDF just means anything that is less than or equal to k. So it starts from 0, 1, 2, and then adds everything up until k. So just remember how to use your calculator. Just remember how to get to these functions, especially let's say you're not using a TI and then you would use like Casio. You would have to know the equivalent functions on those calculators as well. Great. Do you want to just go ahead? Do you want to just go ahead? Okay, great. So now Ella will be moving on to sequences and series.
Okay, hey guys! Now we'll move on to sequence and series, which will be a sweet and short section of the review, and also be the last topic we're going to cover today. So a sequence is an ordered list of numbers that follow a specific pattern or rule. So we can usually denote it as A1, A2, A3, ... While a series is the sum of all those terms in a sequence, in which we usually write it as A1 plus A2 plus A3 plus ... So for an arithmetic sequence, the general term is Tn equals to T1 plus n minus 1 times d, where T1 is the first term, n is the total number of terms, is the number of terms that you want to find, and d is the common difference between each consecutive term.
So general tip is that T2 minus T1 equals to T3 minus T2, which is also equal to Tn minus Tn minus 1, which equals the common difference D. The sum of an arithmetic sequence is Sn equals to n over 2 times a plus Tn, where a is the first term and Tn is the nth term, which is the last term in that entire sequence. This we can also write it as n over 2 times 2a plus n minus 1 times d. This is because we can write Tn as a plus n minus 1d, and then we add another a to it, so we get this. Okay, moving on to sigma notation. So here are some common sigma identities. The first one being that you can take any constant out of the sigma notation. Second one being that you can add or subtract any sigma notation. And then the third one is basically the sum of the first n integers, which equals to n times n plus 1 over 2. And this formula over here is the sum of the first n squares, which equals to n times n plus 1 times 2n plus 1 over 6. And the last formula we see here is the sum of the first n cubes, which equals to n times n plus 1 over 2 and all squared. Alright, and it's important to note that you cannot multiply or divide sigma notation. Okay, now I'll go on to a simple example for arithmetic sequence. So A, find the common difference D. So here D basically equals to 6 minus 2, which is 4. And then B, find the 10th term in the sequence. So T10 equals to T1 plus n minus 1 times D, which means it equals to 2 plus 9 times 4, which equals to 38. And then part C of this question, find the sum of the first 10 terms in the sequence. So S10 equals to 10 divided by 2 times 2 times 2 plus 9 times 4, which equals to 200. Alright, let's next move on to the geometric sequences. So the general term of any term in a geometric sequence is Tn equals to a times r to the power n minus 1, where a is the first term, r is the common ratio, and n is the nth term. So a tip for this would be that a2 divided by a1 equals to a3 divided by a2, which equals to r, the common ratio. And in general, an divided by am equals to r to the power of n minus m. So for the sum of a geometric sequence, Sn equals to a1, the first terms, times 1 minus r to the power of n, and then over 1 minus r, where r cannot equal to 1 because this will make the entire thing undefined. Alright, so let's move on to another example for geometric sequences. So this question tells us that the first 3 terms of a geometric sequence are ln x to the power of 9, ln x to the power of 3, and ln x, where x greater than 0. So for since we know the logarithmic laws, we can move this exponent to the front for the first 2 terms. So this is equivalent to 9 ln x, and then this is equivalent to 3 ln x. This does make the question a lot easier because we can find the common ratio r very easily this way. So part A, find the common ratio. Basically, we can do T2 divided by T1 equals to 3 ln x divided by 9 ln x, which equals to 1 over 3. And then part B of this question requires infinite geometric sequence, in which we'll come back very shortly. Alright, let's look at the notes for this first. So an infinite geometric series continues indefinitely. Whether it has a sum depends on whether it is divergent or convergent. For a convergent series, the term approaches 0 as n increases, and the series does have a finite sum if the absolute value r is smaller than 1. So this is the formula here. the sum of all the terms equals to a over 1 minus r, where a is the first term and r is the common ratio. But we have to make sure that the absolute value of r has to be smaller than 1. And for a divergent series, the terms do not approach 0 as they increase, and the series grows without bound. So for this one, the absolute value of r is usually greater than or equal to 1. And the infinite sum does not converge and cannot be calculated because the terms get infinitely big. Alright, let's look at one example. So consider the infinite geometric sequence for 4,480, negative 3360, 2520, and a negative 1890. So find the common ratio r. So r basically equals to t2 divided by t1. So negative 3,360 divided by 4,480. So this should give us a value of negative 3 over 4. Find the 20th term for part B. So t20 equals to first term, which is 4480, times the common ratio, negative 3 over 4, and then to the power of 20 minus 1, which is 19. And this is a very big number, or it's weird, hard to express this in simpler form, so we simply write as 4480 times negative 3 over 4 to the power of 19. And to find the exact sum of this infinite sequence, we do S infinity equals to a over 1 minus r, which equals to 4480 divided by 1 minus negative 3 over 4. This gives us 2560. Alright, now we're gonna go back to the question earlier. So this one, solve this thing equals 27. So for the first step here is that we can take the ln xl because it is a constant. To 27. And so now we want to try to calculate this, which equals to so here, so for this sequence, t1 equals to 1 over 3 to the power of 1, which is 1 over 3. So S infinity equals to 1 over 3 divided by 1 minus 1 over 3, which equals to 1 over 2. So this simplifies to ln x times 1 over 2 equals to 27. So ln x equals to 54, and x equals to e to the power of 54. And that's our answer here. And here, this is the last question of the day. I'll give you guys like 3 minutes for practice, and we go over the solutions really quick afterwards. let's go over the solution for this practice problem. So for AI, write an expression for the common ratio r. So this could either be 4 over k minus 4, or it could be k plus 2 over 4. Either one will work. So part A, I show that k satisfies the equation k squared minus 2k minus 24 equals to 0. So we basically use this above. So 4 over k minus 4 equals to k plus 2 over 4. You can cross multiply, and then this will simplify to k squared minus 2k minus 24 equals to 0. So B, find the possible values for k. All you're going to do is basically solve this quadratic. K squared minus 2k minus 24 equals to 0. Factor, we get k minus 6 times k plus 4 equals to 0. So k could be negative 4 or 6. Next one, find the possible values for r. So when k equals to 6, we have r equals to 4 over 6 minus 4, which is 2. And when k equals to negative 4, we have r equals to 4 over negative 4 minus 4, which equals negative 1 over 2. So part C says this geometric sequence has an infinite sum. Which value of r leads to sum? This one has to be the r value of negative 1 over 2, because the absolute value of negative 1 over 2 is smaller than 1. And the last part of this question says find the sum of this infinite sequence. So S infinity equals to a over 1 minus r, which equals negative 8 over 1 minus negative 1 over 2. So this will give us the final answer of negative 16 over 3. Okay, and that's all for today's review prep session. We basically covered everything that we planned to cover. All of the notes from today's session will be posted shortly on our Instagram and also on Discord. Anything else? Okay. And tomorrow's session will go from 4:30 to 7:30. Hope to see you guys there tomorrow. Thank you for coming, everyone.